Alright, so good afternoon. Let us continue our lecture on eigenfunctions and eigenvalues. Last time we was discussing that, okay, if I consider the eigenvalue problem like this, and I want Pn to be periodic on minus L to L, right? So P0 will be 1 and lambda 0 will be 0 because you have the second derivative of 0 is 0. And then we also discussed that, okay, if n is sinus of n pi x over L or cosinus of n pi x over L, then lambda n is minus n pi over L squared, right? In this case, you have sinus of n pi x over L is minus n pi over L squared, sinus of n pi x over L, and cosinus of n pi x over L second will be minus n pi over L squared cosinus of n pi x over L. Okay? So let me explain this again. In the previous class, we consider the Fourier basis, right? The Fourier basis is composed of the function 1 and the function sinus or the function cosinus, right? So this is the Fourier basis. The Fourier basis composed of the function 1 or cosinus and sinus, right? So what happened with the Fourier basis? If you take a second derivative of the function 1, you get 0. And I said that 1 is the eigenfunction with respect to the 0 eigenvalue. If I consider sinus or cosinus, all right, I take the second derivative, I'm gonna get minus n pi over L squared sinus and cosinus, which means that sinus and cosinus are eigenfunctions with respect to the eigenvalues n pi over minus n pi over L squared, right? So, but this means that you have a system of eigenvalues and eigenfunctions for this eigenvalue problem. Phi n second is lambda n phi n, and phi n is periodic on minus L to L, right? So this is the meaning of all of the Fourier basis, right? So Fourier basis, their eigenfunction are functions of the problem 1. Right? And the eigenvalue is lambda 0 is 0 and lambda n is minus n pi over L squared. Right? So basically the Fourier basis that is composed of the function 1 and the function sinus and cosinus of n pi x over L, they are eigenfunctions of this problem, all right, with respect to the eigenvalue 0 or the eigenvalue n pi over L squared, right? Now let us try to generalize this idea. So in the previous class, we consider this problem, right? So this problem was considered on 0, 1. And the boundary conditions are phi of 0 is 0 and phi prime at 1 is 0. Right? So this is what we were trying to do last time. So from this problem to this problem, right? So the difference between 1 and 2, 1 and 2. So the first thing is that the domain is not from minus ml anymore. So the domain is no longer symmetric. The domain now is 0, 1. So 0, 1 is not symmetric, right? And the next thing is that, okay, periodic is now changed to phi n 0 is 0 and phi n prime at 1 is 0, right? So we changed the boundary condition and we changed the domain. It's clear? Explain again. So in the previous lecture, we were trying to study Fourier series. The Fourier series composed of the function 1 and the function sinus and cosinus, right? The function 1 and cosinus and sinus, they are eigenvalues, eigenfunctions of this problem. For instance, the function 1 is associated to the eigenvalue 0, because when you take the second derivative 1, you get 0, and this is 0 times 1, right? So this function 1 is associated to the eigenvalue 0. The function sinus and cosinus, they are associated to the eigenvalue minus n pi over l squared, right? Because when you take a second derivative of sinus, you get lambda n sinus. And when you take a second derivative of cosinus, you get lambda n cosinus. Now, let us try to have a problem where we replace the domain by 0, 1, right? So minus LL is now become 0, 1, and the periodic condition is now phi of 0 is 0 and phi prime is 0, this one. So this is 2.3.6 in the lecture note. This is lambda n. Right? In the previous lecture, we were looking at the eigenvalue at the characteristic equation. Right? So the characteristic equation of this equation is x squared is lambda n. All right? So I record you that, okay, suppose that you have a second order differential equation, right? Then the characteristic equation is AR squared plus BR plus C is 0, right? And this is second order differential equation with constant coefficient, and this is homogeneous, right? So you can go back to the book by Haberman. Book. So this is from Introduction to Differential Equation. This is a class that I'm also teaching now in the morning, and we are right now here. So this is the 3000 level class, and this is the book for that class. All right. So to solve a second order differential equation, you look into the characteristic equation, right? Now the characteristic equation of this phi n second is lambda n phi n now becomes x squared minus x squared is lambda n, right? In the last class, we consider the case number 1. Lambda n is strictly positive, right? So when lambda n is strictly positive, we conclude that phi n has to be 0 and lambda n has to be 0. This is a contradiction. All right? So there is nothing in this case, right? So in this case, you don't have eigenvalue and you don't have eigenfunctions, right? Now let us consider case number 2. So this is math 3133. So case number 2, lambda n is 0, right? So when lambda n is 0, so what is the solution of the equation? Sorry? No. Now I can, so the first case lambda n is strictly positive, right? Now I want to consider a case when lambda n is 0. So when lambda n is 0, what is the solution of this guy?
0.
No. Yes?
It was the polynomial from ax plus b. You have to set it up and set it equal to.
Can you sign it up with the paper, please? So when lambda n is 0, right? When lambda n is 0, this equation will become lambda n, phi n, and this is 0, right? When lambda n is 0, lambda n phi n is 0, because this is 0 times phi n, and this is 0, right? So which means that phi n second is 0, meaning that phi n is ax plus b, right? So this is something that we did in our very first lecture. So if the second derivative of the function is 0, it has to be a linear function, right? So phi n x has to be ax plus b. All right. So now, how can I continue? Yes.
I was going to say plug in the initial conditions.
Yes. Can you sign at the back of the paper, please? This is not an initial condition. This is boundary condition. Yes. So this I'm gonna check with the boundary condition. Phi 0 is 0, and meaning that a times 0 plus b is 0. So b is 0, right? So now phi n of x is ax, right? Because phi second is 0, this function has to be linear. So phi n has to be ax plus b. Now I'm gonna check the first boundary condition. Phi n of 0 is 0, implies that a times 0 plus b is 0, which means that b0 is 0. So phi n of x should be ax, right? So what should I do next? Yes?
Take the derivative.
Yes, can you sign at the back of the paper, please? So I'm gonna check the boundary condition for the derivative of 1, right? So phi n prime will be now a. So phi n prime of 1 is 0, meaning that a is 0, right? Clear? So after checking that phi n of 0 is 0, meaning that a times 0 plus b is 0, I conclude that b is 0, so phi n is now ax, right? And phi n prime is now a. I'm gonna check with phi n prime is 0, then a has to be 0. So in this case, we're gonna have phi n is 0, and lambda n is 0. So 0, 0 in general is not an eigenvalue and eigenfunction, right? So you can admit the 0 eigenvalue with the function 1, but if it is 0, 0, then this is not what we want to study because it's too trivial, right? Questions? It's clear? So I explain again case number 2. So case number 1, normally you don't have anything. Case number 2, it depends. Sometimes you can get 1 eigenvalue, sometimes you don't get anything. In this case, you don't get anything. All right? Case number 2, lambda n is 0. When lambda n is 0, you have phi n second is lambda n phi n. Lambda n is 0, so this is 0. All right? Because phi n second is 0, you have that phi n is ax plus b. You check with the two boundary conditions. Phi n of 0 is 0, which means that a times 0 plus b is 0, and which gives you b is 0, right? So phi n now is ax. I'm going to check with the second boundary condition. The second boundary condition says that phi n of 1 is 0. So, which means that a is also 0. In this case, you have lambda n is 0, and phi n is 0. This is not admissible, right? So this is not an eigen. This is not an eigen function. Right. And the most important case is the last case, where lambda n is negative. Case number 3. So we don't have extra homework for this week because we haven't finished all of this. So when we have enough exercise, enough materials, we're gonna have homework, right? Right. So case number 3, you're gonna have lambda is negative. Lambda is negative. So in this case, you have x squared is lambda n, right? So what are the two roots of this equation? Yes?
Aren't we gonna have to use e to the alpha t times cosine beta t plus e to the alpha t sine beta t?
Yes, we are going to do that. But what are the two roots of this guy?
Oh,
But you can say at the back of the paper. This is a good idea. But what are the
X.
yes?
xi minus xi,
Xi minus xi.
or whatever.
E minus lambda n t and e lambda n t.
Lambda n t. No, I'm just asking the root of this equation. Yes?
Cosine minus root n I. Or lambda n I.
Oh, wait.
Lambda is negative.
Yeah, that's what I put the I with.
Yes, but you cannot take the root of lambda n.
I'm confused.
Yes?
Is it I plus or minus root lambda n?
No, lambda n is not positive.
I think it's lambda n I.
No,
I square root of lambda.
lambda is not positive.
Right.
I square root of the positive
I-
number.
So this is what? Can you say it again?
I times square root, I guess it would be the absolute value of lambda.
Yes, so you have to put absolute value. Can you say the back of the paper, please?
Alright.
Lambda n is not positive, so you have to put an absolute value, right? Plus or minus the absolute value of lambda n. Right? Right, so this is like, what is the square root of minus 3? This is I square root of 3. Plus or minus. Right? So there are two square root for minus 3. It is plus or minus I square root of 3. You have to take the absolute value because here lambda n is not positive, right? Now I have this guy. Again, this is coming from solving second order differential equation with constant coefficient. What are the two solutions associated to this guy? Yes?
Something to do with cosine and sine.
Yes, can you say and the back of the paper, please? So the solution will be C1 cosine of square root of lambda n x plus C2 sinus of square root of lambda n x. Alright? It's clear? If you don't remember, so let me write down a formula for this guy. So I consider delta, which is b squared minus 4ac. Right, so this is math 3133. So in this case, if I have ax second plus bx prime plus cx is 0, I have a characteristic equation, a squared plus br plus c is 0. A delta function is b squared minus 4ac. Case number 1, delta is positive. What happens when delta is positive?
Solution.
You have two roots, then
It's not an eigenfunction. I'm sorry, I shouldn't.
yes?
Yeah, repeat it.
Sorry?
The roots.
No, I'm just asking when you have delta is greater than 0. What are the two solutions of this second order differential equation?
X e x minus
X can
x equals e to the minus square root of delta t.
right. So when delta is greater than 0, you have two roots. And so let me because here this x is the variable, so let me called this phi. Right? So in the first case, delta is positive. You have two roots. L1, 2 will be minus b plus or minus square root of delta divided by 2a. All right. In this case, you have two roots, and the solution will be phi of x will be c1 exponential of r1 x plus c2 exponential of r2x. Right? This is our first case that we considered previously, right? In the previous case, you have square root of lambda, right? And minus square root of lambda. This is why in the case number 1, I put c1 exponential of square root of lambda n x plus c2 exponential minus square root of lambda n x, right? Case number 2. Delta is 0. So what happens when delta is 0? Yes?
You have only one solution.
Yes, you have a double root. You have only one solution, which is minus b over 2a. Can you sign at the back of the paper? And now, what is the form of the solution in this case? What?
Bx equals e to the minus b over 2ast.
Yes, 2ax. This is one point, right? So this is one. This is only half of the solution. So e to the power minus e to the r1 x plus c2. There's another component. Yes.
E to the R1, oh, sorry, X, E to the R1X.
Exit, can you say at the back of the paper, please? So, in this case, you have x e to r2x, right? This is why you remember that in this case when lambda is 0, r1 and r2 in our case was 0. So the exponential become 0. This is why previously we have ax plus b, right? Ax plus b, because here when, because in our case r1 and r2 they're both 0. This is why this becomes c1 plus c2x, right? It's clear? So case number 3, which is our case here, delta is negative. So what are the two roots? Yes?
The alpha plus or minus bi.
Yes?
So, then b of x would be the e to the alpha t cosine beta t plus e to
Yes.
alpha t.
Can you sign the back of the paper, please? When delta is negative, you have two solutions, right? So R1, 2 will be minus b plus or minus square root of the absolute value of lambda divided by 2a. Alright? So when delta is negative, you have two roots. Minus b plus or minus square root of lambda times I over 2a. And the solution will be phi x will be c1 e to the power minus b over 2ax cosinus of the square root of lambda over 2ax plus c2 e to the power minus 2b over 2ax sinus of square root of lambda over 2ax. Yes?
In the case 2 equation, should it be like R1 in both
R1.
exponents?
Yes, yes.
Okay.
Can you sign the back of the paper, please? Alright, so this is the formula. I suggest that you go back to this and check and review this method, how to solve a second order differential equation with constant coefficient, right? I explain again. So if you have a second order differential equation with constant coefficient, this is the homogeneous case. On the right hand side you have 0. So you write out a characteristic equation, which is ir squared plus br plus c. You consider delta, which is b squared minus 4ac. Alright? Case number 1, delta is positive. This equation has two roots, minus b plus or minus square root of delta divided by 2a. Then you're gonna get the solution of this form, c1 e to r1x plus c2 e to r2x, right? Case number 2, delta is 0, then you have only one double root, which is minus b over 2a. Phi x will be c1 e to the r1x plus c2x e to the r1x, right? Case number 3, delta is negative. You have two roots that are complex root, right? You have minus b over 2a and an imaginary part. So the solution will be exponential of the real part plus cosinus of the imaginary part, right? So these are knowledge from differential equation class, and I recommend you to go back and review this, because from now on we are going to build stuff on this kind of thing, right? So we are going to use all of this to solve eigenvalues problem, right? So now compare case number 3 here and case number 3 here. Why do I have cosinus plus C2 sinus? Yes?
Alpha in this case is 0.
Yes, can you say at the back of the paper, please? So in this case, right, so in this case, we have x squared is lambda n, right? So which means that A is 1, B is 0, and C is minus lambda, all right? You compare the two equations, right? So this is the characteristic equation that we have here, and this is the characteristic equation that we have here. You see that A is 1, B is 0, and C is minus lambda n, right? Which means that in this case, R12 will be, so the delta will be, B, which is 0, square minus, so this is going to be 4 lambda n. Right? The delta is b squared minus 4ac. So in this case, the delta is 4 lambda n. Right? So the R12 that I have here will be b is 0. So basically, I'm going to have square root of 4 lambda n plus or minus over 2 I, and this gives me plus or minus square root of lambda n. You see, this, the two roots that I computed using this formula here is exactly the same with what we have here, right? It's clear? So in this case, the phi 1, this exponential is going away, so what you have left is just this part plus the sinus. This is why we have this solution. So I explain again another times. So in this case, delta is negative. I have a square plus b plus c is 0. So I compare the two equations. Now a is going to be 1, b is going to be 0, and c is going to be minus lambda, right? The delta will be b squared minus 4ac. So b is 0. 4ac will be 4 lambda, right? So the two solutions will be R12 will be plus or minus the square root of lambda divided by 2a, which is 2. So I get the two roots, which is exactly the same with the solution that we have here, right? So I'm gonna plug. So the b will be 0, so the exponential here goes away. The square root of lambda, square root of delta over 2a becomes square root of lambda. So this is why here I have C1 for sinus of lambda plus C2 sinus of lambda, right? Questions? Right, I recommend you to look back into this how to solve ODEs, because we're gonna solve PDEs based on the knowledge of ODEs, right? So, but basically, for this part of the knowledge, what you have to remember is just this formula, right? The formula here is recommended that you remember. Questions? It's good. Right. So now using this complicated formulation, I arrive at this solution, right? So phi n is c1 cosinus square root lambda n x plus c2 sinus of square root lambda n x. All right. What is the next step? Yes. Yes. Can you say at the back of the paper, please? So I'm gonna plug the boundary condition, right? So I have phi n of 0 is 0. right? So when I plug phi n of 0 is 0, what happens? Yes?
Sine goes to 0, and you're left with C1 equals 0 because cosine.
Yes. Can you sign the back of the paper, please? All right. So let me erase this part. So when Pn is 0, right? So I have what? I have 0 is equal to C1 cosinus of 0 plus C2 sinus of 0, right? I plug 0 here and here. So I'm gonna get 0 is equal to cosinus of 0 plus sinus of 0. But the sinus of 0 here is going to be 0. So and the cosinus of 0 is 1. So basically what I get is C1 is 0, right? So now the Pn becomes C2 sinus of square root of lambda n x. All right? I explain again. After I use the formula that I show, I arrive at this form of the solution, right? So phi n of x will be C1 cosinus square root of lambda n x plus C2 sinus of square root of lambda n x. All right? I'm gonna use the first boundary condition. Phi n of 0 is 0. I plug 0 here and 0 here. So the sinus of 0 is going to be 0. So the cosinus of 0 is 1. So which means that C1 is 0. So I replace. So what is the next step? Yes?
Take the derivative and use the other boundary.
Can you sign at the back of the paper, please? Now I'm going to use the second boundary condition, right? In order to use the second boundary condition, I'm going to take the derivative. So the derivative of this guy is this one, cosinus of the square root of n of x. All right? I take the derivative of this guy, I get C2 square root of lambda n cosinus square root of lambda n x. I'm going to plug 1 there. So you have phi n of 1 is 0, meaning that C2 square root of lambda n cosinus of square root of lambda n x is 0. Right? But I don't want C2 to be 0 because it's going to give you the function 0. So this C2 is not 0. The lambda n is negative. So basically this leads to cosinus of square root of lambda n x 1 times 1 is 0. All right? No? Questions? I explain again. After I use the first boundary condition, I infer that C1 is 0. Now, phi n becomes C2 sinus of square root of lambda n x. All right? It's clear? I take a derivative. This gives me C2 square root of lambda n cosinus square root of lambda n x. Now phi n prime is 0, right? So this means that this is 0. So which means that the cosinus is 0, right? Because the lambda n is not 0 because we are not in the case where lambda n is 0, right? Questions? Now, what is the lambda n that makes this cosinus 0?
N pi over 2.
N pi over 2. No.
It'd have to be, sorry,
Yes.
so it would have to be square root of pi over 2. Sorry, it would have to be pi squared over 4.
Pi squared over. So the cosinus of this has to be n pi plus pi over 2. Right? How do you remember that? How do you remember this is? So what is cosinus of pi over 2? 0, right? What is cosinus of 3 pi over 2? This is 0, right? Okay, so because this is periodic function, so cosinus of 2n pi plus pi over 2 has to be 0 because they're equal, right? Cosinus is 2 pi, periodic function. So cosinus of pi over 2 is 0, means that cosinus 2n pi plus pi over 2 is also 0, right? Now, this is the same for the second guy. So you have cosinus of 2n pi plus 3 pi over 2 is 0, right? So how can I write this in a different form?
N pi plus n pi over 2.
Yes. N pi plus n pi, no. Yes?
N pi plus.
So this is 2n pi plus pi
Yeah.
plus pi over 2, right? So this is 2n pi plus pi over 2. Yes?
This would be 2 pi over 2.
No, this would be cosinus of 2n pi
And
plus
pi
1
over 2, sorry.
plus pi over 2 is 0. Alright?
Be n pi over 2.
Right. So now you combine this and this. So basically you have cosinus of n pi plus pi over 2 is 0. See the point? Right? So in the first case, cosinus pi over 2 is 0, meaning that cosinus 2n pi plus pi over 2 is 0. So here you are dealing with the even numbers, right? 2n is an even number. Now you have 2n pi plus 3 pi over 2. So 3 pi over 2 is pi plus pi over 2. So you can combine this pi with the 2n pi and you have 2n pi plus 1 pi plus pi over 2. So basically here you have pi over 2, here you have pi over 2. Here you have all of the even numbers. And here you have all of the odd numbers, meaning that you can put both of them to be n pi plus pi over 2. Right? Good? Clear? Yes?
Wouldn't it be easier to write it as n pi over 2 though? Because it would essentially be the same, right?
Now n pi over 2 is not the same with this one because you're gonna have n pi over 2, right? So you're gonna have n is 4. So I pick n to be 4.
Got it.
So this gives me 2 pi. And cosinus of 2 pi is not 0. Right? Cosinus of 2 pi is 1. Right, so which means that the square root of lambda n has to be n pi plus pi over 2. It's good. Right? So in this case, lambda n has to be n pi over 2 squared. Right? So what is the value for lambda n? Yes?
Negative.
Yes, let me sign the back of the paper. You have to remember that lambda n is a negative number, right? Because here we are in case number 3. So lambda n will be the minus of this guy. Will be minus n pi plus pi over 2 squared. Right? So what is phi n in this case? What is phi n in this case? What is phi n? You just replace lambda n here, right? So phi n will be C2 sinus of this guy. So basically this gives me sinus of n pi plus pi over 2 x. Alright? These will be the eigenfunctions. And this will be the eigenvalue. Right? Now I'm gonna put everything here and I'm gonna summarize. So in this case, all of the function phi n such that phi second is lambda n phi n. Phi n of 0 is 0, phi n prime and 1 is 0, is the sinus phi n will be sinus of n pi plus pi over 2x, and lambda n will be minus n pi plus pi over 2 squared. Right? Explain again this part, right? So from this part, you see that, okay, after I replace the first boundary condition, I get C1 is 0, right? Now, C1 is 0, phi n will be C2 sinus of square root lambda n x, because C1 is already 0. I use the second boundary condition. To use the second boundary condition, I have to take the derivative of the function. So the derivative gives me C2 square root lambda n cosinus of square root lambda n x, right? So phi n of 1 is 0. I replace 1 here. I have C2 square root lambda n cosinus of square root lambda n is 0, meaning that cosinus is 0. Cosinus is 0 means that the square root of lambda n is n pi plus pi over 2. This is coming from here, right? So this is something that you better remember. So the square root of lambda n is of this form, means that lambda n is minus n pi plus pi over 2 squared, because lambda n is now negative, right? You plug this lambda n back into the form of phi n here. You plug this back into the form of phi n, you're gonna get phi n is C2 sinus of n pi plus pi over 2x, right? This is a constant, so I can remove it. So now I'm gonna get the eigenfunctions and eigenvalues, right? Questions? Now I'm gonna check this again, right? Right? So to compare with the Fourier series that we have here, the Fourier series are defined from minus L to L. This is why we have to shift as one of the practice exam that we did when we want to represent a function in terms of the Fourier series. The first thing. The second thing is that the boundary condition is periodic in this case. But the Fourier series satisfy the condition that that if you take the sinus, which is one of the eigenfunction, you take a second derivative, you still get back the sinus, right? Except that you have a factor that is coming out. So this factor is called eigenvalues. The new functions that we found, they have very similar properties, right? But they are defined from 0 to 1. Boundary conditions are different. So phi n at 0 is 0, and phi n at prime at 1 is 0, right? And now if you take this derivative of sinus 2 times, you're gonna get sinus again with this factor. Let us check. Right, so let us check this first, right? So you have sinus n pi plus pi over 2x prime. So you're gonna get n pi plus pi cosinus of n pi plus pi over 2x. Alright? Now I'm gonna take the second derivative, so I have sinus of n pi plus pi over 2x prime minus n pi plus pi over 2 sinus of pi plus pi over 2x. Alright, and then you have a square. Right? So this is very similar to the Fourier series that you have. You take a second derivative of this function, you get the factor. And this is called the eigenvalue. Right? So this is eigenvalue. And this is the eigenfunction. This is exactly like here, right? So those are eigenfunction. And this is eigenvalue. Right? This is exactly the same. And again, in all of the exercises, you will see that, Rima, what can you say about this function? This is still the sinus and cosinus function, except that you put a different constant here, right? Right, so basically this is the same. So this is the modified of the sinus and cosinus function here, except that here you have a different constant in front of x. In this case you have n pi over L, and here you have n pi plus pi over 2x. In all of the exercises that you will do in this class, you will encounter sinus and cosinus function again. The only difference is this constant, right? And because of this constant, you're gonna have different eigenvalues and different eigenfunctions, right? Yes.
For this example in specific, then, are we just not concerned with solving for C2?
Good question. Can you stand at the back of the paper, please? All right. So because here you don't any C2 should work, right? So I put C2 here. Suppose I have put C2 here. Here is still C2, and here you still have C2, right?
Yeah.
So if this is an eigenfunction, you multiply that with the C2, it is still an eigenfunction. So the C2 is not important. It's just a it's just a multiplier, right? So you multiply this function with a constant. This is the same.
So it'd be like just the amplitude of the signal.
Right. So here is also the same, right? So if you, in the Fourier series, if you multiply this with 3, you still have 3, right? But in the AN, you have to divide by 3. So it's going to be the same. So we don't care about that constant.
Okay.
Right, so the C2 is not important, so I don't care about the C2. And the eigenvalue is different. The function is slightly different from this. So you still have sinus and cosinus, except that you multiply with some different weight in front of x, right? And the important thing is that for the Fourier series, you need periodic functions. Here you don't have. You have different boundary condition, right? So let us check phi n is 0. So I have just checked the first condition, which is the eigenvalue condition. Now I'm going to check the second boundary condition. So phi n of 0 will be, I have sinus of 0, right? Sinus of 0, and this is 0. This is good. So the second, so this is checked, and this is also checked, right? So the next one is phi n prime of 1 is 0. So in this case, phi n prime will be n pi plus pi over 2 cosinus of n pi plus pi over 2 x, right? I take the derivative of phi n, I get n pi plus pi over 2 cosinus n pi plus pi over 2x. Now I replace 1 here. So phi n prime at 1 will give me n pi plus pi over 2 cosinus of n pi plus pi over 2, right? So this is 0. And basically you get also 0. So the second boundary condition is checked. All right? So there are two important things. The first thing is that you move from a symmetric domain minus L to L to 0, 1. And the second thing is that you change the boundary condition, right? You change the boundary condition from periodic to these two boundary conditions. Phi n of 0 is 0 and phi n prime of 1 is 0, right? And because of that, you have different function that are modified function of the modified version of the Fourier series. You still use cosinus and sinus. You always use cosinus and sinus, but you put them some different way, right? Questions? And another important thing is that for the Fourier series, these functions are given, right? So you know them in advance. You know that those are the Fourier bases. Everyone knows that they are sinus of n pi x over L and cosinus n pi x over L. For this case, you have to compute. You have to compute by yourself, depending on the problem that you want to solve, right? Now, let's try to solve a problem. Any questions on this? So this is the modification of the Fourier series, and this is not given. This is something that you have to compute. And in order to compute that, you have to remember that table that I just wrote. Any questions? It's clear? Now let us try to solve one example that we have. So this is still 2.3.6. Um, 2.3.6, you want to solve u second is equal to 2. And u0 is 0. Ux of 1 is 0. This is the PD that you want to solve, right? You find, this is find u. All right? In this case, you want to solve the equation u second is equal to 2, and we know in advance that, okay, u at 0 has to be 0, u at x. U prime, this is u prime, 1, has to be 0. All right? So given those set of functions, right? Given that phi n prime second is going to be lambda phi n, and phi n of 0 is going to be 0. Phi n prime at 1 is going to be 0. Right? In which phi n is sinus of n pi plus pi over 2x. And lambda n is minus of n pi plus pi over 2 squared. Right? So this is a set of eigen functions. And we're going to mimic what we did for the Fourier series. So what should we do in this case?
We could take u double prime and integrate it twice.
No, but you have boundary conditions. You need better idea. Yes?
We find u equals ax plus b.
You want to write u as an times this basis. Right? So you want to use it. Can you say at the back of the paper, please? Right. Right? So n here is going to be from 0, 1, 2, 3. All right, so we're going to do something similar to the Fourier series, right? So ux is the sum when n is going from 0 to infinity of an of sinus of n pi plus pi over 2x. All right? I'm going to use this form. Is it clear? This is the modification of the Fourier series. So remember that in the Fourier series case, you have ux is a0 plus the sum of an cosinus of n pi x over l plus bn sinus of n pi x over l. Right? And it's going from 1 to infinity. Why is it? Because those functions are the eigen functions, right? So you just expand u in terms of all of the eigen functions. Yes?
How does that work if it's not periodic though?
This is for periodic function, right?
Right.
Because all of those functions are periodic. In this case, you don't have periodic function,
Right.
right? But those functions are not periodic. So, but there's something, this is a very good question. But the boundary condition of the phi n and the boundary condition of u, they're the same, right?
Okay.
This is a very good point. Can you sign the back of the paper, please? Now, let us check the boundary condition, right? So you have u of 0 is, how can I compute u as 0?
Just put 0 here.
Yes?
Just plug the 0.
Yes, I plug 0 here, and it's going to be 0, right? So n is going to be 0, and sinus of 0, and this is going to give me 0 because sinus of 0 is 0, right? So basically, the key point is that if you want to study periodic function, you have to use cosinus and sinus because these functions are the eigenfunctions of the periodic eigenvalue problem. Yes?
So I get why we're using sines or interval, but why don't we use the A naught at the front? Because it's not.
It's I naught is here, right? So here I naught is outside, but because here you have cosinus and sinus, but here I have I naught, so I put a 0 inside. Right? So this is like I naught outside plus n 1 back infinity. It's the same. Right? So now I'm gonna check u prime at 1. And you're gonna see that they have the same boundary condition. What is u prime of x? Yes?
Is it just cosines, but with the inside like divided by the or times the an?
Yes. Can you say it? So u prime of x will be the sum when n is going from 0 to infinity, an of n pi plus pi over 2 cosinus of n pi plus pi over 2x. Alright? And the u prime at 1, what is the value of u prime at 1? 0, right? Because this is 0. So this is the sum when n is going to 0, infinity times n pi plus pi over 2 cosinus of n pi plus pi over 2 times 1. So this is 0, so everything will be 0. Right? So you see the point? So if you want to find a periodic function whose second derivative is equal to something, you want to use the Fourier series because all of the components here, they are coming from the periodic boundary eigenvalue problem, right? But in this case, you have different boundary condition. You have u0 is 0 and u prime 0 is 0. So you have to put the boundary condition into the eigenvalue problem, right? It's clear? So in the previous case, cosinus and sinus, cosinus of n pi x over 2 and sinus of n pi x over 2 are solutions of phi n. Second is lambda n phi n and phi n periodic. So u is periodic, right? So in the Fourier series case, the cosinus and sinus, they're solution of the eigenvalue problem with periodic boundary condition. This is why you can expand periodic function in terms of all of those functions. In this case, you want a function which is not periodic, but you have a very special boundary condition. You have u0 is 0 and u prime at 1 is 0. This is why you still have to keep this guy, but you have to change. You change the boundary condition. So here I change the boundary condition so that the boundary condition here is the same with the boundary condition here, and the boundary condition here is the same with the boundary condition here, right? Now I solve this one, and as we solved before, we know that this is sinus and lambda n. So u has the same boundary condition with these functions. So I can write it this way. And again, I can check if I write it this way, u at 0 will be 0, and u at prime at 1 will be 0. So it's going to be good. It's clear? Questions? Right? So now suppose that I want to solve something like this. u second is equal to 5, right? U of 100 is 0, and u prime at 100 is 0, and u at 0 minus of is 0. The eigenvalue problem. What is the eigenvalue function problem that I need to solve? Right? Suppose that I want to solve u second is equal to 5 with this boundary condition, right? So what is the eigenvalue problem that I need to solve?
I think you would need the one that has the cosine factor, like the negative, because they're negative, right? Does not affect the outcome.
So this is from minus 100 to 0. So the interval is from minus 100 to 0, right? So the eigenvalue problem will be phi n, second is lambda n phi n. First thing is always the same. The second thing that needs to be changed is phi n at minus 100 is 0, and phi n at 0 is 0, right? So you solve this problem, then you can expand this function in terms of all of those functions. It's good? It's clear? Questions? Right, so basically the Fourier series is for periodic functions. But if you have other functions with different boundary condition, you need other basis, right? Other boundary condition for the eigenvalue problem. It's clear? Right. So now I compute this problem. I have sinus and sinus of n pi plus pi over 2x, and the lambda n is going to be this one. So I expand this u on this basis, right? So then you check that u0 is 0 and u prime as 1 is 0. Good, right? So right. So but now because I'm interested in u second. So what is u second?
We're going with just what the derivative is so far. It's a negative n pi plus pi over 2 squared plus the summation we got for u of x.
Yes. So can you say at the back of the paper, please? If you want to take the second derivative, you take the second derivative of the sinus. But the second derivative of sinus will give you lambda, right? So you have u second of x will be the sum when n is going to 0 to infinity. An sinus of n prime plus pi over 2x second, right? But this satisfies this eigenvalue problem. So basically, what you do is you just have to multiply everything with lambda n. Lambda n of sinus of n pi plus pi over 2x. Right? So if you want to take a second derivative with u, what you do is you take the second derivative of the function sinus. The second derivative of the function sinus will give you lambda n times the function sinus because of this guy. It's good because sinus n pi plus pi over 2x second is minus n pi plus pi over 2 sinus of n pi plus pi over 2x. Alright? So far so good? Right. So any further questions? So let me summarize. Before I try to solve this problem, let me summarize the following things for you. Right? So if u is periodic on minus L to L, right? the basis that we need to use is the basis is Pn second is lambda n Pn, and Pn is periodic, right? And this is the Fourier series. Good. So for a periodic function, you need to consider the Pn second is lambda n Pn, and Pn is periodic, and Pn is the Fourier basis, right? So Pn in this case will be 1 cosinus of n pi x over L, and sinus of n pi x over L, right? This is basically the meaning of the Fourier series. Clear? Now, if U is not periodic, but U is not periodic, satisfying U at 0 is 0, and U prime at 1 is 0, right? So this is on 0 to 1. Good. So what you do is that you change the boundary condition of the eigenvalue problems, right? So the basis will satisfy Pn second is lambda n Pn, and phi of 0 is 0, phi prime at 1 is 0. All right. The basis will be this one, and first the Pn will be those functions, n pi plus pi over 2x. It's clear, right? So you can express functions on a basis, and you can compute that basis, right? So in the Fourier, so if you have a function which is periodic from minus L to L, the Fourier series said that you can expand this function on the basis that you have here, because this is the eigenvalue problem associated to the periodic boundary condition, right? In our case, the U, without looking at this equation, you look into the boundary condition, right? The U is defined on 0 to 1 with two boundary conditions, U0 is 0 and U prime at 0 is 0. Then if you want to find a basis for this function U, right? The basis will be computed by this equation. Pn second is lambda n Pn, and Pn at 0 is 0, Pn of prime at 1 is 0, and Pn will be sinus. Questions? Right. So because U satisfy this boundary condition, I can write like an sinus of n pi plus pi over 2x. Right? So like in the Fourier series, except that you replace the Fourier basis by some other sinus function. Of course, because all of the Pn satisfy this boundary condition, the U has to satisfy this boundary condition. Now I compute U second, right? I compute U second by computing sinus second. Sinus second will give you lambda n times sinus, right? It's clear? So what is the next step? Yes?
Set U double prime equal to 2 and solve for A of M.
Yes. Can you sign the back of the paper, please? Now you have to expand the number 2 on this basis, right? So we have to expand. So expand and number 2 as the sum. So we have to expand the number 2 on this basis. So the Bn, n is going from 0 to infinity. Our Bn, sinus of n pi plus pi over 2x. Right? Right?
What I got so far.
Yes. So suppose that I have all of Bn. Of course, Bn is something that we need to compute, right? But suppose that I have the Bn. how can I compute an? Yes?
N would be equal to Bn divided by lambda n.
Yes, can you say at the back of this? Right. So suppose that you can expand this, so you can identify the coefficient of the sinus on both sides. Right? So Bn should be An lambda n. So we will do a lot of exercise on this so that you understand how to compute it. All right. So suppose that you can expand the number 2 in terms of all of these bases. Then you can identify the coefficient, and then An times lambda n has to be equal to Bn, and An has to be equal to Bn over lambda n. Right? Now I need to compute this Bn. Yes?
But you can only get lambda n from solving Bn.
You can get lambda n.
I don't know, I'm just a bit confused. So
No, lambda n is given, right? Lambda n is minus of n pi plus pi over 2 squared.
Oh, okay.
All right, so this is lambda n. Right, so because you take the second derivative, you get lambda n. Right, so basically this is Bn dividing by minus n pi plus pi over 2 squared. Right? It's clear? Now, how can I compute Bn? Yes?
Could Bn, since x would just be a factor and it would multiply, wouldn't sign always go to 1, so couldn't Bn just be 2?
No. Because this means that what? This means that you have B0 sinus of pi over 2x plus B1 sinus of, so this is 1 pi plus pi over 2x, right? Plus B2, 2 pi plus pi over 2x. And you continue forever, right? But to compute Bn is going to be similar to compute a Fourier coefficient. How do you compute that? So suppose that you have a Fourier coefficient. How do you so suppose that I have mx is going to be a0 plus the sum when n is going from 1 to infinity of an cosinus of n pi x over L plus Bn sinus of n pi x over L. Right? So this is the Fourier series. So how do I compute Bn?
You do 1 over L times the interval from, or I guess it would be from 0 to infinity, right?
So
Or something.
So you inner product f with this sign, and you didn't divide by side sign. So it's gonna be f, the integral from minus L to L, fx sinus of n pi x over L, divided by the integral from minus L to L of sinus of n pi x over L squared. All right? Here it's going to be the same, except that you change the interval, right? So Bn will be the integral from 0 to 1, because we are from 0 to 1. So I have 2 inside, times sinus of n pi plus pi over 2 x dividing by integral from 0 to 1 of sinus of n pi plus pi over x squared. Right? Here, you multiply f with the function that contains Bn, right? And you integrate, and then you divide by the integral from minus L to L of that function square, right? Good. You remember this? Yes.
So why is the bottom squared again? Just the denominator, why is it squared?
Yeah. No. So this bottom square will give you 1 over L.
Oh, okay.
Right? So the bottom square will give you 1 over L. N pi x over L. And this bottom square will give you 1 over L. Remember that? Alright? So this is, so remember that how we compute that, because all of the guy over there, they're orthogonal, right? So when you multiply f with the other, when you integrate f, you have what? Sinus of n pi x over f on the x, right? Because sinus is orthogonal to everyone except itself. When you multiply f with sinus, right? You're gonna get Bn sinus of n pi x over L times sinus of n pi x over L. Integral from minus f to L. This is why you have to divide by sinus squared. Right? So it is also the same with the case where you have u is a1 e1 plus a2 e2 plus a3 e3. So to compute a2, for instance, you're going to have to multiply u with e2, but you have to divide by e2 times e2. Remember this? Right? So this e2 e2 is like this. Because when you multiply the sinus with this series, this one will go away, this one will go away. The only thing that is left over is this sinus, right? So here is going to be the same. Right, so I explained it again. Right, so I have 2, which is equal to this series, right? Now I multiply 2 with sinus of n pi plus pi over 2x, and I integrate from 0 to 1. Now this gives me b0 sinus of pi x over 2 times sinus of n pi plus pi over 2x, right? Plus bn integral from 0 to 1 sinus of n pi plus pi over 2x times sinus of n pi plus pi over 2x. Alright? The other terms go away because they are orthogonal. So the left over is this guy. It's good? Questions? So it's like it here, right? So when you multiply u with e2, you have what? e1 times e2 plus a1 plus a2, e2 times e2 plus a3 times e3 times e2. Right? So this is orthogonal, so this go away, this go away. Right? So the left over is this e2 times e2. So a2 has to be equal to u times e2 dividing by e2 times e2. Right? So here is going to be the same. Here I haven't checked that those eigenfunctions they are orthogonal, but I'm going to check that they are orthogonal in the next class. But so basically you can compute Bn using this formula, right? We're going to do a lot of exercise on this so that you get, you still have 1 minute, right? It's good, right? So by doing this, we can compute Bn the following way. So the first integral from 0 to 1, 2 times sinus of n pi plus pi over 2x. Yes. So how can I compute this integral?
You pull the 2 out front, right?
Mm-hmm.
I can pull the 2 to the front.
Yes.
And then it would be, you would integrate to use that, which is negative cosine.
Right.
And then you just
So I have 2 times cosinus of n pi plus pi over 2x divided by n pi plus pi over 2. And you evaluate 0 and 1.
It would be negative.
Negative. Thank you. Right? So and 0, this is going to be 0, right? And 1 is going to be 0 is 1. Right? So we're gonna continue this on